All right, recording is rolling on this post facto video for back to Friday, March 25th. Now the internet was not working that day, so I'm making this later saying this is what we ended up doing. Now this was pretty much the plan for my honors students, my AP students. We needed some internet activity access for AP Classroom, so instead I just went ahead and ran this for all my classes, and that ended up working out pretty well. Got to recap Archimedes principle for everyone, including AP. Right, so some things we're looking at materials and states of matter. So we're looking at supercritical fluid. This is if you get temperature and pressure high enough. It actually materials usually go into the supercritical phase where it is ambiguous as to whether they are gases or liquids. A little bit of properties of both. And we looked at non-Newtonian fluids, so fluids that maybe don't follow the normal conventional physics that you would expect for fluids to follow. There's technical details on that, but an example that we could do right in class was to make some cornstarch and water. You get an example of a non-Newtonian fluid where it flows around like a fluid until you apply a pressure to it, and then it provides a resistive force, kind of like properties of a solid. Interesting, right? Got that. And then we spent some good time in class looking at how could you calculate the density of this object right here. It's a little bit more dense than water. So if I fill this beaker with water, drop this in, it'll sink to the bottom. How can you figure out what is the density of this? Now, I pulled up the notes that I had drawn up back on Friday. Actually, let me start with this. There's actually a historical story this links back to, going back a couple thousand years ago to ancient Greece. And according to legend, it went something kind of like this. There was this king of this Greek city-state who was given this crown that was purported to be gold, but the king's kind of suspicious. I don't know, is this thing really gold? Now, one way you could tell if something's gold or not, well, maybe it's like related to its density, right? Each material has an associated density. And okay, so if they can only figure out the density of this material, then they can compare that to gold, and that might be an indication of whether it was made out of gold or not, or maybe it was, maybe some alloy mixed down with other metals. So density is mass per unit volume. So mass, that's easy to get. You just throw this on a scale. Volume, well, if there's some geometric shape like a cube, you could just do length with height, or I guess even this shape, right? You could measure the side and then figure out the area of this triangle, then multiply by this depth and get the volume that way. So mass per unit volume, maybe you could do that. But what about like a crown? That's a funny type shape, right? So the story goes that this was tasked to Archimedes, who went home and said, okay, I'm gonna sit down in the tub and think real hard about this. And as he's lowering himself in the tub, he watches the water level rise. And at that point realizes, oh, the change in water level represents the displaced volume. Well, that's the same thing as the volume that is submerged, like as I lower myself into the tub. So you could look at the displaced water level, that displaced volume, to get the volume of the object, submerged object, then take the mass rating from the scale, divide by that volume, mass per unit volume. That could be the density of the object. That's how you get the density of some funky 3D shape like a crown. And if legend is true, this is the point that he was so excited by this revelation, Archimedes was, that he jumps out of the tub and runs naked through the streets, shouting Eureka. So that'd be one way to do it, right? Get the mass of this object, maybe by putting on a scale. Maybe if since I gave you guys spring scales back on Friday, maybe hang the spring scale. I'm reading this as having a weight of 0.3 newtons. So the corresponding mass would be about 30 grams, somewhere there, right? Pretty close to, right? And then divide by its volume. Maybe you could fill this with water, look at the displaced volume and divide those two, mass per unit volume, and get it that way. Okay, so that's where the volume of the object would, of course, be V2 minus V1. Right? That's one way you could do it. Now, you might be looking at the speaker though, thinking, I don't know, maybe the water level would change by somewhere. I'm looking at the tick marks here. We're looking at like 250, 275, 300 milliliters, 1 milliliter of water, the same thing as 1 cubic centimeter. Maybe think, I don't know how accurate that would be. How maybe I really want like a pretty good accurate calculation for what's the density of this material. So there's a roundabout way, really tricky way we can apply some tricky physics and maybe get a more accurate reading of the density of this material using only the spring scale and the knowledge of the density of water. Ooh, okay, I'm still gonna have a beaker full of water, but we're not gonna use the displaced volume method. We're gonna use something a little bit different. So let's look at a free body diagram for this object submerged in the water. So here's what I did. I hooked this here. Remember I said it weighed 0.3 newtons. Say I fill this beaker with water, dunk this in here, and the scale reading goes down to like 0.05 newtons. So that might indicate maybe like a 0.25 Newton force. And here's the free body diagram that would be associated with that. So this object has a weight hanging in the air, it pretty well reaches its weight. Maybe it's a tiny force from buoyant force from the air, but basically negligible. Right? Density of water is 1,000 times what it is of air. So now you're getting a pretty good buoyant force if it's submerged in water. Now, since you guys know that if it's in equilibrium, some of the forces has to go to zero, I could rearrange this and get something like this. This buoyant force would be the difference between the weight and the spring force as it's submerged. So F sub S for the rest of this proof is going to be the spring force as it's submerged in water. Okay, so we got that. And now, but you guys know something else about buoyant force though, and that's Archimedes' principle. Going back to that guy with the crown of the tub. Archimedes' principle says this, that the buoyant force is equal to the weight of the water displaced. Now here's how it breaks down into this expression. Density of water times the displaced volume of water, well, that would represent the mass of the water displaced multiplied by the gravity field you're in. That's the weight of water displaced. Paul Hewitt did this too, filmed himself as he displaced some object. He caught the water that would run over and weighed it and exactly turned out to represent the buoyant force. Okay, so now we have two different perspectives on buoyant force. We've got Archimedes' principle, okay? And we've also got this free body diagram method where it's the difference between the actual weight of the object and the spring scale reading when the object is submerged. Okay? So we can set those equal to each other. It looks like this. And you can calculate the volume based on the weight of the object and its spring force reading. But now you have to know the density of water to make this happen too. That's embedded in Archimedes' principle. But maybe this is a bit more accurate way to get the volume, which means that when you get density, right, density of this, well, I'll call it glass, density of glass object, take mass divided by volume. Right? Now we have a calculated volume. Let's do some substitutions. So the mass of the object would be its weight. That's to say if you just hang it at spring scale, I'm getting about 0.3 newtons. Okay? Just hang its weight divided by the gravity field that you're in. Right? So there's the mass of the object, right? And then the volume of the object. Well, that's this crazy expression I got from combining Archimedes' principle and free body diagram from involving spring scale, submerged in water. Right? Get this volume. Okay? So I'm looking at fraction divided by fraction. Now, you probably remember from math class, fraction divided by fraction, take the bottom fraction, flip and multiply it. So A over B all divided by C over D is equal to A over B multiplied by D over C. Ooh, little switcheroo down here. Hey, that looks like the format that this is in. So I'm going to take this bottom fraction, flip and multiply. Oh, okay, that's where this is coming from. See how this goes here, this goes here, this gets copy pasted right here. And lo and behold, the gravity field cancels out, which is a good sign that you are on the right track. Because remember what this expression is supposed to represent density. And we're doing this experimentally involving a spring scale and dunking in water. And the density of this object, well, that's a material property, which should be independent of what planet that you do this experiment on. I mean, if I take this whole spring scale in water up to the moon or to Mars or back to Earth, it shouldn't matter where I do this experiment. I should get the same density material. And by gravity field canceling out, that is a good indication we're on the right path. Okay. Now the other G, gravity field, that's embedded in the weight, which is spring scale reading. Maybe instead of G, I should have said like gravity force, like weight, something like that. All right, next step. So that simplifies to look like this. Now I can plug in the values. Remember I said the hanging weight was 0.3 newtons and the spring scale weight when it was submerged was all the way down to 0.05 newtons, right? Which maybe an indication this was just barely more dense than water, right? Because anything more dense than water is going to sink all the way down the bottom. Oh, speaking, that was one of my side questions back on Friday too, is anyway, run the numbers. This ends up being, say, 1.2 gram per cubic centimeter or 1,200 kilogram per cubic meter. It's a little bit more dense than water. So what if you take this out to the Pacific Ocean and you drop this in the Pacific Ocean? what's it going to do? Is it going to go all the way down to the bottom of the ocean? Or is it going to go about 3/4 way down and just kind of stop there? And the answer, well, if you're at home watching this video, maybe you want to pause and think about that. But here's the answer right here. The answer is it's going to go all the way down to the bottom of the ocean. So there is more and more pressure increasing as you go down, but pressure increases linearly, and there's always more. I should say the difference in pressure is always going to be the same because it's scaled linearly all the way down. Yes, yeah. Anything more dense than water will fall all the way down to the bottom. Now, since it's just a little bit more dense than water, that's showing up why the spring scale grading was significantly less than the weight, because there's pretty good buoyant forces. So last piece I want to put in here to round this all together. What is the density of water? Well, it's pretty well exactly 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. So 1 gram per cubic. Remember, properties of metric system are scaled according to properties of water. That's why these numbers work out so nice even exactly 1.00. And now if you're, say, working with small materials, or maybe you're in chemistry, you might prefer to use units like this, like gram per cubic centimeter. What is 1 gram per cubic centimeter? Let's say you take a 1 centimeter by 1 centimeter by 1 centimeter box, right? Little tiny box right here, and fill it with water. How much mass would that water be? Well, 1 gram, right? Because it's 1 gram per cubic centimeter. Versus if you did a different perspective on density of water, let's say you use actual base SI units like we've been using in this class since August. You might want to use kilogram and cubic meter, because kilogram and meter are the base units of mass and linear distance, respectively. So 1 cubic meter, look down the floor, see floor tiles, 3 floor tiles is pretty close to a meter. It's a little bit short of a meter. So go 3 floor tiles by 3 floor tiles by 3 floor tiles. It's a little bit smaller than, say, 1 meter by 1 meter by 1 meter. We're making 1 cubic meter box, a big old box, and then fill that with water. What would the mass of that water-filled cubic meter box be? Well, it would be 1,000 kilograms. Probably too heavy to pick up even. It's crazy. But think of its ratio multiplied by density of water, get the density of the material, and bigger. That's how you can get the density, calculate the density of this material using spring scale and water to submerge it in, but not necessarily relying on trying to read volume changes. Now, of course, if this was accurate, you could just do mass per volume, but if you're not so sure about the volume change, or what if you have a lake and you're just submerging this in the lake, it's like, okay, well, water level doesn't really change perceptibly at all, right? You can use this method right here and get the density of the material. All right, so that was the challenge back on Friday. Fun was had by all, and yeah, moving on.